Let's go through LeetCode 440, case smallest in lexicographical order. For this question, it is asking us the case lexicographically smallest integer in the range from 1 to n. So let's look at example 1. So k equals 2. In G, we are looking for the number from 1 to 13. The second one, so it is 10. We are going to return 10. We know for this kind of question, there is a similar question, which is 386 lexicographical numbers. It lets print those kind of lexical number, those numbers in lexical order. And we know we can traverse and do the pre-order traversal to compose the result. But this will be O n time complexity. Apparently, for this kind of data range, we are not able to traverse all of the data out. And also, it is just asking the case number. It's not ask us to print all of the number. So we should do it in beta time complexity. So um, for but the way doing 386 can give us some kind of hint that those kind of numbers they are in some kind of tree. It is like a chart tree. 1, 2, 3, 4 to 9, right? So we'll see this chart tree has a child from 10 to 11 to 19, right? And in this level, this has 20 to 29, and this one to be 90 to 99, right? And so this is layer 1, and this is layer next layer, right? So after this, there is a 100 and to 109, right? And this one will be 190 to 199, right? So for this tree, every layer it will have the counts about 10 times of the previous layer. So the same thing about here, right? So this is from 200 to 299. And this one will be 900 to 999, right? So we are looking for the case numbers in these chart trees, and also there is an limitations. So what we can do is that we use um, we can use prefix. So what does this prefix do? Prefix. So this prefix initially, let's set this as 1. And also we use the p index initially set as 1. So what is this prefix do and what is p? This p is how many numbers have we walk past this kind of chart tree before. Um, so for this prefix, so we are trying to and trying to see for this kind of prefix, it is trying to simulate it to target the case lexicographical number. So we are trying to have the prefix to be targeted to the number as when we go through this P. So how can you do that? So that is let's look at the process. The prefix initially is 1, right? So we can have a count with this prefix. How many numbers, lexical numbers in a range, right? So for example, if we have a count of this tree, there is 100, 1000, there are, for example, and there is about 100 and then 11, right? In this kind of trees. And we find for this kind of trees, for example, we have the target K is 200 something, 237, right? So we'll see this 111 is not enough for all of these kind of subtrees. But if we go to the next layer, right, it will be 1111. It's already exceed this. So we know it must be in this kind of layer, but 111, the whole tree is not enough. So let's look at the second one, right? The second one has another 111, right? So we have two. So we'll see the counts for this one is the second one is actually not 111. It's being cut, for example, two cut to 237, right? So being cut somewhere here. So it may have some kind of number, for example, I don't know what's the number, possibly, for example, 99 or those kind of number. We add this one, right? And then if, for example, the prefix 1 and 2 doesn't fit, it doesn't get to K. We add this to our P, right? P doesn't get to K. That means um, it must be in a later subtrees, right? So for example, we count if a prefix starts with 3, if we add that, for example, we added some kind of another number, for example, possibly 80 or something, right? We found it already, the P is more than 237. That means our number should be sitting in this subtree, have a prefix 3, right? So then we repeatedly doing this process, for example, 3, 1, right? And 3, 2 until 3, 9, right? So for 3, 1, and it has a child 3, 1, 3, 1 to 3, 2, right? It has child, there is 1 only, right? In a 311, right? 311 is already been cut off. So if, for example, we find this P being already been added to 135, right? And here, and we find that this has only one numbers, and 235 that will be um 236, and 333 will be the, maybe that will be the 237, right? So this example may not that good because it doesn't have that much of a layer. The problem is that we should what we want is that we want to count every subtrace, right? And count every subtrace how many what is the biggest P we can go far. Then we know if, for example, we find it's from the third third subtree, right? Three, the prefix which is 3. Then we go to 3, 2, for example, it has some kind of numbers, right? It's not enough. If this done enough, we go here, right? Until we meet some kind of subtrace, we find it is more than the P is already more than K, right? Then that means we should go to, for example, this is 3, 4. And then we try to find this is 3, 4, 1 and 3, 4, 2, right? Until find another one, 3, 4, 3, 4, 5 or something. Find this one is already more than that. Then we um, we continuously hitting, right? Hitting the the subtrace, right? So for example, let's set the n to be some bigger number so we can has multiple layers, right? So the process is that we cut all of the prefix, for example, the bigger prefix with 1 first, 2 first, until we find the prefix, for example, the third, 3, right? Then we on the 3, we have prefix 3, 1, 3, 2, right? And 3, 3. we cut those kind of counts from here, right? So what we cut is the first step, cut the count here, cut the count here, and we found the count here is already more than k. Then we go to its subtrace, then cut here, cut here. For example, we found the 3 is more than k. Then we recursively to cut, for example, 331, 332, right? Cut the subtrace until we find the p equals k. Then our prefix is our result, right? So let's write code for this. Um, we are going to have int p equals 1 and a prefix equals 1, right? So let's comment. This is p will be what does p mean? Let's comment here. The p is we can say p is how many numbers we worked past so far, right? Through our chart tree. And what is the prefix? That is the current node we are sitting, right? That is actually the current node we are sitting. Okay. So then what we do is that while this kind of p is smaller than k, right? Then we need to have a help function called count equals get count. Then that will be prefix n, right? So that means in this kind of prefix for this kind of prefix subtree, right? What's the counts of the number smaller or equal to n, right? So there are two scenarios. One is p plus count is greater than k, right? That means this prefix is we are sitting in this prefix subtree. Then we have prefix should multiply equal to 10, right? We go to the next layer, and also because our this kind of p number should increase by 1, right? Because we move a number. Else, if p plus count is um, smaller equal to k, right? Then um, then what we need is we need have our prefix to its next siblings, right? So what does it mean is that for example, all of these counts doesn't have enough, right? So that 1 is not enough. Then it needs to go to 2, right? Or for example, we have 3, right? 3 we have 3 1. We find 3 1 is not enough. Then we go to 3 2. So this is it goes to its siblings, right? And also because it goes to the siblings, we'll have p should plus equal to the count, right? We just count this kind of prefix, how many, this will be the counts, right? Counts. So our p should add all of these counts. So when we jumping out of this while loop, we just return prefix. Okay. So we need a have function, private int get count. That for this kind of prefix, let's try and see whether we need a long or not. Prefix is 10 to the I think possibly int should be enough, right? Possibly because prefix and prefix 10 to the power 9 and n is let's use the int, trying to see whether it's enough int prefix and int n, right? So what we do is that we have int count equals their current equals the prefix, and next will be prefix plus one, right? This is it's a sibling. So what we have is while this current is smaller equal to n, we're going to have a count should plus equal to mass dot mean n plus one, and next minus current, right? And we should have current should multiply by equal by 10, and next should multiply by equal by 10, right? And so return count. Um, so So that is we are looking for this kind of subtrees, right? That may have limitation of n somewhere here, right? And for this prefix, we just this next it is on the other tree, right? Sibling other trees. So this is current, right? So every time we have current multiply. So for example, this is 2. This next will be 3, right? So current, for example, goes to 20. Then next is going to 30. So it has 10 counts here, right? So if go to next layer, for example, this is 200. This is 300. So this has another 100 counts added to our result, right? It is possible we need to change this current next to be long because 10 to the power 9. I'm not sure. Let's try to sum it to see if it can pass. This kind of range, yeah, I think this will be out of the integer range. Let's put current counts all these kind of variables to be long. And I think and also doing like this should be because the 10 to the power 9, right? And we are count to the next layer. So integer the max, let's see, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 to the power 9, right? But when we calculate this tree, we have a we are going to have current goes to tens, right? So let's use long. But when we decrease, right, the maximum will be 10 to the power tens. So here, because you see this one, for example, 10 to the power tens, right? Uh, because it goes here will be 10 to the power 10, right? So this one will be 10 to the power 9. So let's use a long so that it will be not exceed the limit. So doing like this, we'll see we are trying um, to get rid of these trees, right? So for example, this is 1111 numbers and get those kind of trees. So this kind of operation, it is a log 10 uh, an operation trying to count how many nodes in this kind of trees, right? Which of course we have a limitation smaller equal to n. And this is a log operation. And this while loop is also doing a log n times. So that will be n log n square time complexity for the process. The space is O1 constant. And we need let's also write the Python code for this. So we need a P in a prefix. Let's set this one as 1 and 1, right? So what we have, while P is smaller than K, we're going to have count equals, we'll need a function called get count. Um, so we have a prefix. Of course, we need to have the n to limit it. So we'll say if P plus count is greater than K, right? Then that means uh the number is in this prefix subtree. Then we're going to have prefix should multiply by equal by 10, right? And also we have P should plus equal to 1 because we moved one node. And we'll say else, that means we need to go to its sibling. So we'll have prefix should plus equal to 1 and P should plus equal to count. Right? We're jumping out of the while loop. We just return prefix. And we need define get a count, right? So we have self prefix. This is the int, and this is the int. We get its count is the int, right? So we need a count and a current and the next prefix, current prefix. Next, let's write this equals 0 prefix and the prefix plus 1, right? Then we'll say while this current is smaller than smaller equal to n, we'll have count should plus equal to mean n plus 1 and next prefix, right? Minus current. And we should have a current multiple equal by 10. And the next should also multiple equal by 10, right? So in the end, we just return count.